So in this video, we're going to talk about recursive function and inductive proofs. And this is one of the key concepts in an algorithms class. And I think this concept is going to help students familiar with recursive function and how we can reason and try the proof of correctness for these types of functions. And this is a very good introductory in algorithms and how do we solve these functions. So what is the recursive functions? A recursive function is a function that it calls itself and it solves a smaller problem of itself. So here in the code example, we have a function of trying to calculate factorial of a number that we input in. So here we can see that this function, it calls itself at the end for n minus 1. So that simple is it. So what is the problem with these kind of function? Um, the idea is that we're trying to solve a problem with a smaller problem, but when do we need to stop solving for smaller problem? When do we need to stop calling itself and actually solve it? And it may loop forever. Let's say, for example, this is a bad factorial function. So in this back factorial function, we take a number of n and we keep decreasing the number. And here we have a base case for the code when to stop solving the problem. But if we input a bad number like an odd number, then this number is gonna be an odd number and it keep decreasing by two, decreasing by two. It would never be zero. So this piece of code will loop forever and may not and never execute. So this is a bad example of a recursive function. So we being a being in the course of algorithms, we're trying to teach you how to prove every algorithms that you introduce. So inductive proof is a mathematical tool for reasoning, and this is a very useful tool for you to proof of correctness for every recursive function. Let's go through it. So in inductive proof have three cases. We have base case. We prove that the statement is true for a specific number, usually one. So these statements are usually easy cases that you can naturally see it at simple cases. And the second step, we have inductive hypothesis. We assume that the statement is true for some value k. And the last step is we have inductive step. We prove that the statement is true for k plus 1 using the assumption that it is true for k. So let's go back to the function factorial. We try to calculate factorial of n, and let's see how this function is a correct function. So the proof, as we see before, we have base case. We have factorial of 0 is 1. So this is the base case. Factorial of 0 is we return the value to be 1. And inductive hypothesis, we assume that factorial n calculates the right answer for the number n factorial. And inductive step, so for every inductive step, we're trying to prove for the next step, which is correct. So we're trying to prove that factorial of n plus 1 is correct. And we have the calculation of n factorial based on the hypothesis, the inductive hypothesis. So let's calculate factorial of n plus 1. Here, if we input n plus 1, we replace n with n plus 1. So at the return, you're going to return n plus 1 and factorial of n plus 1 minus 1, which is factorial n. So here in this return case, it's going to return n plus 1 times factorial n, and we, according to the inductive hypothesis, we know that factorial of n is actually it gives the correct answer. So this is the formula we have to return. And it turns out this is the formula for n plus 1 factorial, right? So in this case, the we proved that the base case we actually usually done we terminate the function, and then we also know that the return value from the function is also a correct number. So let's see again the inductive proof. So we have the base case. We prove the statement is true for a specific number, usually 1 in the case of factorial function is 0 because we have a simple fact in math that factorial of 0 is 1. So we usually use very simple cases. And then we have inductive hypothesis. We assume that the state is true for some value k. And then on the inductive step, we prove that the statement is true for k plus 1. So we prove the statement is true for k plus 1 using the assumption that is true for k. So we're building up in the inductive step, we're trying to build up the correct formula using the previous cases. And then it's have an inductive effect that until the base case, which is naturally true, you keep building the right answer for your problem. So the main idea is we can solve super simple cases. We solve a big problem by solve smaller problem of itself. And we leverage computing power from computers and coding skills to solve a problem for a very big number for ourselves. So what other problems can we also solve using this idea, using recursive function and inductive proof? We can also use merge sort, which is an idea to sort an array in ascending order. In this case, we also have an array, but we also sort in a smaller array. And then when we combining them together, we have sort the array in a faster manner rather than the usual cases of the classic sorting problems are of n squared. And using merge sort, you splitting those problems smaller problems, and we sort themselves inside them, and we're gonna have a sorted array in an ascending order in the better runtime. So we can also have a graph traversal algorithms like depth first search. This is also a technique that you're gonna traverse, that you're gonna search through a data structure called tree or graph that very useful when you catch up to the graph algorithm section. And this is okay. Sure.